Can you hear me? Huh? Oh. Hello? Okay. I'm I mean, this is not from me, because clearly this is working. See me? It's not me. What if I do this? The what? I don't know what the button is. Oh, it's on. You know. Yes. Isn't nice of me. Oh, I'm gonna fix this forever. At least it's on. I don't know what to do. What am I? No, it's all dead. Why, baby? All right. Good. If you have a question, just let me know. All right. I don't know. Any administrative? No? 1, 2, 3, 4, 5. You can also use the mic. So yeah. Anyhow. So yes. So last time we talked about that Newton's method should have failed. So we had this example, x cubed, which has no minimizer. Okay, so this is the function. And it went like this. And it has no local min yet. Newton method gave xn converging to 0. Okay, so Newton method should have failed and it did not. So let's look at another method. Yeah, if you are going to statistics, you will see this pretty soon. It's called method of steepest descent. And it's one of the base of neural nets. Okay, so all the pictures I'm taking are from neural nets. Okay, so this is the foundation for all the cool stuff that's happening in stats. Most of the cool stuff. All right, so before I go into this, let me remind you. Or do I? Okay, I say here. Good. You start with the function, and we talked about last time or a few weeks ago that the gradient is normal to the level set. And so that was one thing. What was another? Oh yeah, we had the directional derivative, right? So we had ddv, no, ds of f, x naught plus sv. This was equal to the inner product of the gradient with v. In other words, gradient of f cosine theta. And we said that when you're moving in the direction of the gradient, when v is gradient of f, then theta is 0. Yeah? Because their angle is 0, so cosine of theta is 1. So this is the maximum. Yeah? So the maximum directional derivative is when you follow the gradient, and minus of it is called steepest descent. Okay, so that's what people care about when you have this the biggest decrease in your derivative. All right. It turns out that you have to be more careful, and we will do some simulations. You can't just move minus gradient. You have to move minus alpha gradient, where alpha large, we will show later, means you make big jumps. Okay, so this is, let's say this is your, you pick your V, and you pick in what direction to move in the domain X. Okay, so if you move too far, if alpha is too big, you move too far and you might skip the minimizer. But if you move too little, you might never get there. Okay, so we'll do simulations of this. So the method is start with an x naught, and then move in the direction where your gradient is negative. So in other words, let's do 2D. Suppose this is x star. Suppose this is xn, and then you have, I'll do it with a parabola like this. This is, that will throw you off. Okay. Let me teach you something before we go on. So this is called contour plot, okay? Because we will need to use this. So you have a 3D surface, yeah? And then we push it down, okay? So when you push it down and you look from Z, you get a bunch of circles. So This is the origin, this is X, this is Y, and you get a bunch of circles. Okay, these are the level set of the function. So F is 1, F is a half, F is 1/4, whatever. You understand? Is that okay? All right, good. So when people draw these pictures, so if you Google gradient descent, you will often see the following. So this guy has a minimizer at 0, so it's right at the center, and you will see something like this. And what people do is they say, okay, start from x0 and then move in the direction of x0 minus the gradient of f, evaluated at x0. And since the minimizer is at 0, your vector will throw you towards 0, okay? Because you're just adding a vector that points to that. So and then, yeah, this is x1, and then it keeps going till it hits 0. So, okay, because x star is just the origin. All right, so questions? All right. Right, yeah. So you can even figure around with AN, the step you make, because you can imagine, here's your contour plot. If you start from x0 far away, just give me a little bit of freedom. Let me take A to be 100. So I jump right in here, but then I have to be careful so that I don't overshoot. Yeah, all right. Okay, and of course the question is, how do you pick this alpha? So, yeah, so you want to be close to the minimizer, so overshooting, you know, just means you moved past even the next step. So let me explain. So again, how do we pick alpha? Because this is confusing. So you start with some point xn, and you want to pick a jump. Okay. You want to pick a jump alpha, but if you go back to your picture with the parabola, you want to, and this is the min, right? You want to jump so that you're still below this line. Okay, you don't want to jump and you go up here, right? So this is this min. Okay, so you have to stay below that line. That's what it means to overshoot. Okay, so call this value C, and you don't want to jump above this value C. Okay, all right, good. So that's how you pick alpha. And right. So yeah, okay, anyways. What else? Yes. Okay, now I want to talk about this alpha. I should do the simulation. So yeah, I mean, this is the 1D example, right? The minimizer is at 0, and over here, so this J function is just x squared. And I took this picture from online, but it was a nice picture showing the alpha. And yeah, so exactly, if you pick your alpha too big, you risk. So let's do the example actually. Why am I keep talking? So take x0 to be 1, and then what is your method? x1 would be x0 minus alpha, and then derivative of x squared, which is just 2x. Yeah, okay. So you have 1 minus 2 alpha. But now, right, but how do you pick alpha? You want this guy when you evaluate it. So you want f of x1. So 1 minus 2 alpha squared. You want this guy to be less than the previous step. So you have f of x0. So 1 squared, right? Okay. So what do you have? This is actually easier because here all you want is you just want 2a to be bigger than 0, right? Unless yeah, so this is not, are you sure? Oh, no, you need absolute value. Yeah. So you want 1, 2a, 0 like this. Okay? So that's the constraint for a. If you pick it bigger, you risk not minimizing. Okay? Do you understand? It's very simple. Oh, doesn't it always work with a? Yeah, like I said, Michael. So here, if I pick a bigger than a half, I risk overshooting. Like in this picture, he overshot. So let me see. So he starts from, yeah, you see from here, he overshot. That's an overshot. Okay, Michael? All right, good. Okay, now some stupid simulations. Yeah, so how do I rotate? Yes. So this is our graph. And we started from an initial point, and then the gradient descent just kept moving down, and then he made a turn. So now let me show that in, yeah, okay, good. So then this is the contour plot. It goes down, and then it zigzags to 0. Okay. It keeps running, actually. And yeah, and then, what was that? I picked different alpha, yeah. Yeah, this is the one. So here I picked different alpha, and you see the red one is the slowest, and the purple one was the fastest. Okay, so you see the red is still hasn't converged yet. The purple one, yeah, the purple one is there because I just picked. You see my out. If you see, I don't know if you can see it. So I don't know. There's an alpha up there. It says 0.5, 18, and 22. You see up at the corner? Yeah. Okay. So that's what's going on. 20 alpha was the biggest, so he went the fastest. So I'll give you that code after on the website to play around. I mean, that's the main idea, all right? There's nothing, the hard part is picking alpha, and I'm gonna prove you convergence theorems based on alpha. So let's do that. So again, gradient descent is very simple. The k plus 1 step is equal to xk. If you like, plus the direction of decrease. Okay. Yeah. And like we said, we picked alpha to minimize the possible jumps. Okay. So here, S, yeah, anyway, S is a generic number. But remember, this alpha k was picked so that it minimizes the right-hand side. So let me write it again. This is equal to the min of, let me use different variable, not to confuse you, y positive of f of xk minus y, and then the negative direction, okay? So we're just bound by one of them. And again, just to remind you, right? I'm just trying to prove decrease, because otherwise this method is meaningless. All right, so why do we put that S there? Because we want to take directional derivative. So I'm just repeating the proof of greatest decrease from a month ago. So what did we do? We took derivative and we had that you get the dot product, inner product, right? So I'm just repeating the proof. It's not really. So, okay, so we have this negative. Now let's use mean value. Or okay, I do it by hand, fine. So, where am I? Yeah, anyhow. So this one says that the derivative decreases. So you have that f, call this function g of s. And you have the following result. You have that dgs at s equals 0 is negative. Okay, right? So that implies that g of 0 is a, what do I want to say? Yeah, so the function is decreasing. So this guy is bigger than the one after it. So bigger than GS locally. And just take this one over here, f of xk plus 1. The G, yeah, whatever. Okay, so this and then this. Okay. So this guy showed that, this guy shows that G of 0 is local max. Okay. And then I take one value close to 0. Put epsilon, I don't know, whatever you like. Because this one was proved for every value. Okay. Okay. So let me repeat what happened. Our alpha was picked to minimize over all possible jumps. So then I just bound by one of the jumps. Okay, call it S, the S jump. I take derivative in the S jump. I prove that the derivative is negative. Since the derivative is negative, it means that it's a local max. Okay, so it drops, derivative is dropping. Okay, local mean, derivative is increasing. Anyhow, so so we get that this is negative, so the initial value is a local max. So then just take any s from the neighborhood of the local max, right? That's what local max means. You can pick a guy from there. Is the dot product step of the proof meant to be known a priori? The dot step. Oh yeah, we actually that was the definition. That's how we actually, let me remember. Yeah, you should look back at first week's material. I went over the directional derivative. So I have DDS of x plus SV. Okay. I proved that this is equal to the dot product of gradient with V. Okay, so this is, I think, week 1 or 2. Probably 1. Okay, good. All right, so that was it. And the heart of the proof was this gradient descent that we talked about already. And that's why gradient descent converges or minimizes. Convergence will come later. Okay, so yes, we have two methods, gradient descent and well, yeah, gradient descent and Newton's method. And let's compare them. In gradient descent, you move along the gradient, but like we talked last time, Newton's method is root finding, has nothing to do with has little to do with the function itself. And so so Newton's method is faster because you're just solving a polynomial. So this one is, we proved last time, was faster because we assume that f is C3. You don't have to assume that here. So f, you only want derivative. Okay. So because we assume C3, we had a faster convergence. Okay. Because your function is more nicely behaved. It doesn't have crazy fractal behavior or whatnot. Okay. All right. So yeah. Yeah, that was the definition. Another thing, again, this is a review in a sense. The jumps that we make using, yeah, they're perpendicular. So the vectors, they're vectors, and they're perpendicular to each other. So this would be +2. Okay, so where are we saying? Yeah, okay, let's go through the proof and do it. So again, what are we trying to prove? We're trying to prove that once you go from xk to another guy, xk +1, and then to another guy, xk +2. What's a good way to draw this? How do you draw differences? It was a nice way. So you have this is the sum, and then you have to reflect. So let me do it this way, and then it's like this. So that's okay. It will make it more confusing. Let's do the proof. Okay. All right. So yeah, I'm going to prove to you that this product is equal to 0 if and only if the gradients are 0. Okay. So here I'm just plugging in the definition, so I know what xk +1 is, minus xk +2, and same with this. So there's nothing new here. So I'm using that xk +1 minus xk is equal to minus ak gradient of f at xk. And I take the dot product. Yeah. Something's funny here. Why am I writing it? This is very bizarre. This should be 1 and 2. I don't know why. If the first entry is not 0, then you have that this guy is not 0, right? Because gradient is not 0 by assumption. So again, just to remind you, when we talk about gradient descent and in Newton's method, you need your derivative to be non-zero. You don't want to have flat region, right? So we talked about this last time that when you have flat region, you can't really, you're stuck. The next step is equal to the previous one. So you're stuck in a thing. So that's why, so the middle step here is that gradient of f of xk plus 1 is not 0. Okay. Okay, by assumption. Okay, so we always have that, right? Yeah. And yes. Yeah, okay, so let me explain what happened. So I have more, whatever, let me do it. Do I have more? I have more, okay. So let me do this. So we know the above implies the two, right? So, okay, so these two are not 0. And I mean, each one of them, okay? Like this guy is not 0, this guy is not 0. And we know the AKs are not 0. So we have the following. If this dot product, call it V1, V2, is 0, then we get that the product of f xk plus 1 and of f of xk has to be 0, right? Because the ak plus 1, ak are forced to be non-zero. Okay, that's all. So yeah, I want to draw some pictures for this. What is this? What am I proving? Oh yeah, I'm gonna prove to you that the steps are perpendicular. Yeah. Okay. So again, by definition, the jump was defined like this. So you want to make the minimum jump so that you don't pass the line. So you stay there, and yeah. So since this is the minimizer, we proved from before that local min implies a first order condition. And yeah, so this is 0. Okay. So let's analyze this. So what does it say? So again, from first week, this is equal to the inner product of the gradient of f at xk minus ak gradient of f of xk. Call this guy y. Yeah, I mean, this is the y. And then the vector. So the vector here is, this is xk plus s minus gradient of f. Okay, call this guy v. Okay, so you have this, and then, so which gives you this, and then what was the trick? Oh, right. But by definition, this guy here is xk plus 1. So by definition, this is xk plus 1, and yeah, so, and this is 0. So let me do it from here. So this is 0. So we get that this is 0. So we get that the jumps are 0. Okay, so what's a way to visualize this? So if you Google online, you will see that all the jumps move like this. So this is xk, goes like this, then it goes down like this, and it goes down like this. Okay, so that's what it means. So if you remember, I should zoom in. Can I zoom in? It's hard to zoom in. Let me run it again. Not this one. Yeah, so the jumps, I wish I could zoom in. It's very annoying. Because I made the line so thick. Jeez. I made it like 10. Let me make it smaller. Make it 1. Anyway, so I don't know if it's obvious. I mean, okay. So when you start getting closer, you start making the jumps, perpendicular steps. You see? This is supposed to be 90 degrees. It goes like, all right? So that's what we proved mathematically. Okay. All right. So what was the, yeah. Okay. All right. Next. Take F to be this. Take your sequence from gradient descent. That's your algorithm. Just to remind you, compact set, we defined it as the set where every sequence has a convergent subsequence. So closed and bounded was one, but it's also every xn in K has x and K converging to some x star. Okay, so we're gonna use this. And we will prove the most interesting result of this stuff is that it actually converges to the stationary point. Okay, so Newton's method is root finding, gradient descent is finding the stationary points. All right, good. Let's go. XK is a sequence in a compact set. So there's a subsequence that converges to some number, and we will show that gradient of this guy is 0. Yeah, so suppose not. Yeah, what happened here? So we did this calculation before. The directional derivative evaluated on some vector is equal to the gradient of the guy dot product with that vector v. Okay, so this is the vector v. And we talked about this being non-zero because by assumption, yeah, we just assumed that. So we will get a contradiction, right? So we want to get, we'll get a contradiction. All right. What else? Right. So again, the way we pick the jump is so that it minimizes this guy. So this is a, what do I want to say? Yeah, I know. So derivative is dropping. So you have a local max. So this again implies that at s equals 0, we have local max. So it tells you that f of x star is bigger than some little perturbation, right? Local max in a neighborhood. With a gradient. And we know that this guy is bigger than the min over all possible jumps. Okay, all right. So that's how you get this. And by this was the definition of the jump. Okay. The definition of continuity is as follows. So we're using the following. If yn goes to y, then f is continuous. When f of yn goes to f of y. And by compactness, we had that the subsequence converges to x star, so we can swap limit and function. So that's basically the definition of continuity, that you can swap it with a limit. Okay. All right. What else do I want to? Oh, right. Yeah. And we just proved that this guy is less than the candidate minimizer. So now let's go back to our previous result, but we just proved that gradient descent decreases. So we proved that when xk plus 1 is equal to xk minus ak gradient of fxk, then f of xk is bigger or equal than f of xk plus 1. Okay? Remember, we proved that a few slides ago. But then do this here. You have f of x1 bigger than f of x2, f of x3, blah, 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 blah. And then as you take the limit, you end up with f of x star, right? Okay. So now let's put the two together. Yeah. So you just put one of the steps, all these parentheses. Yeah, so let's go up a bit. So here, so again, we assume it's not zero. That gave us a strict negative derivative, so we have local max. And that gave us that the limiting guy is bigger than the jump. Okay. Okay. So you what shall I say here? Anyways, yeah. So it's bigger than this jump. And yeah, so then here we use the following. So this is a little bit tricky. So it says this is the min over S positive f of x ki minus S gradient of f of x ki. So how did we get this middle inequality? Any ideas? Huh? Set, yeah. So, oh, there's a question. Does C1 satisfy for continuity? Yes, C1 means f is continuous and gradient of f is continuous. And yes, this is a minimum, so you can upper bound by one of the values as a minimum over all s, so you can just bound by one of them. Okay, but then we just we proved this from before, assuming that the gradient is strictly negative or non-zero. And so we have this, and we have this, and we have strict, and you can't have that, right? You cannot have f of x star is strictly less than f of x star. That's a contradiction, because it's strict. Good. All right. So that's all to say that the gradient descent converges to the stationary points, because assuming otherwise gave us a contradiction. All right. What the problem is with descent, like I said before, Newton's method assumes FC3. Descent only needs C1, so naturally it goes a lot slower. It's annoying that we have to find the optimal jump each time, but that's what it is. And now let's do a remaining time. I'll do an example, and I might finish it next time. So take this function, and we will apply gradient descent because it's easy to compute. Yeah, order your eigenvalues. Q is positive definite, so if you take double derivative and it's symmetric, you end up with a Q. Okay, there's no Q transpose because there's a half, so you get Q transpose plus Q divided by 2, but it's symmetric. Okay, good. And yeah, and also what's the gradient? The gradient was, I'll just copy what I'm doing. So it's like Q of X minus B equaling 0. So this is Q inverse B. All right. So I'm supposed to find this. Supposed to find it with a gradient descent. All right. Okay, I don't know how far I will go with this. So, yeah, so let's consider this function. And I don't want to, how much do I have? Okay, it's fine. I'll continue next time. Doesn't make sense. Okay, thank you.